Okay, this is going to be our review session for exam 4 that would cover chapter 7 and 8. So let me go over some of these questions or types of questions that you'd expect in the exam. So one of these questions would be on sizes of electron shells. So sizes of electron shells. What is the electron shells? Those are nothing but principal energy levels, n equals to 1, n equals to 2, n equals to 3. Now, this problem is coming from chapter 7, and question number 15, 12th edition of the Brown-Lemay book. Basically, the question is asking for n equals to 3 principal level or shell in argon and krypton. Would both of them have the same size, or one of them would be smaller than the other one? Let's examine that by simple picture. So this is the central nucleus with protons, and then let's draw 3 shells. 1, 2, 3. So this n equals to 1, that's for shell 1. N equals to 2 for shell 2, n equals to 3 for the third shell. Let's consider that this is argon. And argon, if you look at periodic table, atomic number for argon is 18. That means it has 18 protons. So 18 protons means plus 18. So at the center it has plus 18 because of the 18 protons. Now let's draw the same way for krypton. So in this case, krypton, if you look at periodic table, would be atomic number is 36. That means krypton has 36 protons, or plus 36. So n equals to 1, n equals to 2, n equals to 3. This is n equals to 1, n equals to 2, n equals to 3. Now let's assume that there is an electron sitting in n equals to 3 in both argon and krypton. This is krypton, by the way. So krypton has 36 protons, that gives positive 36. Argon has 18 protons, gives plus 18. From our common sense, we know that having 18 protons, and in this case having 36 protons, there is a difference in attractive force. 18 protons attracting the electron sitting at n equals to 3 would be less than attracting electrons sitting at n equals to 3 when you have 36 protons. So because of the greater attraction, these electrons get closer. So whole shells, the shells of 1, 2, 3 get much closer to the nucleus. So let's redraw these. So this is not the right size. The size for krypton is going to look like this. So this is krypton plus 36. No, I'm just writing on plus. This is n equals to 1, n equals to 2, n equals to 3. So between these two, n equals to 3 shell is going to be smaller for krypton than in case of argon. So final answer is this is larger for argon. So argon 3s is larger than krypton smaller because of larger number of protons in the nucleus. And you have a smaller number of protons or positive charge in the nucleus. So in this case there is a greater attraction, and that attraction brings electrons closer to the nucleus, giving it a smaller size. So there will be a question like this in the exam. Next type of question would be on sizes of atoms. This will be pretty straightforward. It goes like this. If you're looking at a periodic table, tapering end of a funnel. You just bent it and it looks like this. As you are coming from the right side of periodic table to the left, size is getting bigger and bigger. As you're coming down, it gets even bigger than that. Okay, so you get some of the largest atoms towards the bottom of periodic table. Okay, so you just remember this. So the size increases. Size increases. So if you look at periodic table and come from right side to the left side and go towards the bottom, you get larger and larger sizes of atoms. Like, I can give you a simple example. If you're looking at periodic table, and I encourage you to do so, lead is at the bottom, and then you have tin, Sn, and then you have germanium, and then you have silicon. Say silicon is somewhere here. So if I give you these elements and ask you which one will be largest in size, this is towards the bottom. This is largest. And this is going to be the smallest. So basically you need to know how the size of atom changes as you come from right side of periodic table to the left and go towards the bottom from the top. So this is about sizes of atoms, which is question type 2. Then sizes of ions will be third type of question. Now I mentioned in my lecture note 3 cases, and you may have questions from each of those cases. In case 1, same number of electron, different number of proton case. B, same number of proton, different number of electron. C, ions from same group. From same group of periodic table. So let's first consider the first type. Same number of electrons is called isoelectronic. And I often ask this kind of questions, giving you different ions and ask you which of these are isoelectronic. Isoelectronic means same number of electrons. For example, if I have Cl minus and K plus, if you look at periodic table, when you take away 1 electron from K, or when you add 1 electron to Cl to get Cl minus, to get the same electron configuration. This is also a question given in chapter 7, number 35A. So I think it's number 35A, chapter 7. So they are isoelectronics, same number of electrons. Now, how many protons do you have here? Again, looking at periodic table, atomic number is 17 for Cl, and you have 19 for potassium. Number of electrons is same, 18 electrons, 18 electrons. So that's how you should be thinking about this problem. Now the question is, which of these 2 ions is going to be smaller and which one will be larger? You can come up with this answer exactly the same way that we came up with answer the previous one about subshell or shell. 19 protons attracting 18 electrons. 17 protons attracting 18 electrons. You have greater attraction here. So greater attraction means it's going to bring electrons closer. So this would give a smaller size to K plus, and Cl minus is going to be larger. Keep something in mind. Proton-electron attraction tends to give a smaller size. A smaller size. Electron-electron repulsion tends to give a larger size. Even though you see the combined effect, here repulsive part is about the same because they have 18 electrons, 18 electrons. So only difference is proton-electron attraction because of increased number of protons. My next example would be chapter 7, number 28. That's coming from chapter 7, number 28. You need to explain the following. I minus, size of I minus is greater than size of I, which is greater than I plus. If the same element, so same number of protons, the number of protons would be 53. So 53 protons, 53 protons, 53 protons. Number of electrons, since this is minus, there is an extra electron beyond number of protons. So 54 electrons. Same number of electrons as protons, so it would be 53 electrons. And here you took away one electron from neutral. So neutral had 53, so this would be 52 electrons. Now, pay attention to the fact what is changing here and what is remaining fixed. Number of proton is remaining fixed, but number of electrons is changing. 52, 53, 54. The largest number of electrons means the more repulsive factors. Electron-electron repulsion tends to give a larger size. Now why is that? Electrons try to stay away from each other. So when they try to stay away from each other, sizes are determined by electrons around the atom. So when they get away from the nucleus, then it gives you a bigger size. So this would be the largest, having largest number of electrons, and this would be the smallest. And that checks out. So that way you can explain the size variation of ions. Now third kind is pretty straightforward. So F minus, Cl minus, Br minus, for example. FCl, Br, they're coming from the same group. F minus, and then Br minus is the largest, then Cl minus, then F minus. In fourth type of problem, I would ask you to identify reaction for ionization energy as well as electron affinity. So reactions for ionization energy and electron affinity. F plus electron, F minus. This would represent electron affinity. So basically, in order to understand what is electron affinity or a reaction is going to give you ionization energy, you look at what you begin with and what you end up with. Fluorine, we're adding an electron. So if it shows an attraction for electron, it would make F minus, and amount of energy given off would be electron affinity. What is ionization energy? Sodium, you're getting rid of sodium. One electron you're getting rid of, then you get ionization energy. And this is the first time you're knocking off an electron, so it'd be first ionization energy. Next time I knock off an electron, I get Na plus 2 plus electron would be second ionization energy, so on and so forth. Third time it would be third ionization energy. So you should be able to recognize which one is first ionization, second ionization, and which one is electron affinity. Now, fifth type of problem would be coming from lattice energy. So lattice energy, again this is coming from a problem chapter 8, number 26, Brown and LeMay book. So they're saying that NaCl, lattice energy, is this greater than rubidium chloride, greater than cesium bromide. So why sodium chloride lattice energy is so much larger? If you think about the sizes, you'd get the answer. Sodium would be smallest among all these three. Remember, sodium is from here in periodic table. Then you have rubidium and then cesium. If you look at periodic table, you see all these elements. So this is the large one, this is the smaller one. So you have a sodium plus, if this is the size, this is Cl, Cl minus. Let's draw next one, cesium, much larger than sodium. So let's draw it like this, cesium plus, and Br minus is larger than Cl minus. So look at the distance between Na and Cl and between Cs and Br. Larger separation. Remember, lattice energy is determined by attractive force. When there's a large separation, there is smaller attractive force. So there's a smaller attractive force, and that's why lattice energy is much smaller. This is shorter, distance is shorter, they're closer, so there's a much larger attractive force. So smaller separation, larger lattice energy. Larger separation, smaller lattice energy. In this case, it just happened we had the same charges. I may have plus 2 in one for one ion, then it will be greater attractive force because of plus 2. So you'll have to examine this carefully to find out variation in lattice energy. So this was fifth type of problem where we need to compare lattice energy of different ionic compounds. So that's lattice energy for ionic compounds. You need to know also electronegativity. That's also pretty straightforward. By looking at periodic table, electronegativity. This is how electronegativity increases. When you look at periodic table, as you're going up and then go to the right, electronegativity increases, except noble gases. So leave out noble gases. So except noble gases. So we leave out noble gases. So what kind of question I may ask you? I may ask you like sulfur, oxygen, fluorine. Sulfur, oxygen, fluorine. Which one is most electronegative? So sulfur is somewhere here in periodic table, and then you'd have oxygen, and then fluorine would be towards right, that's fluorine. So obviously fluorine would have the largest electronegativity. So these are the qualitative type of questions you have, where you don't need to calculate anything. One of the most important type of problem that you have in this exam would be Lewis structure. So there will be quite a few questions on Lewis structure, resonance, bond order, formal charge, and let's go over these. So Lewis structure. Again, I'll pick one. I'm going to pick one problem. That's chapter 8, number 47, D. Oops. The question is on H2SO4, sulfuric acid, the Lewis structure for sulfuric acid. In order to get this answer, first you need to get the valence electrons. If you look at hydrogen, it has one valence electrons. It's the outermost electron. That's the valence electron. And I have two hydrogens, two sulfur. You look at periodic table and count from left to the right, only S and P electrons in order to get a valence electron for sulfur. Sulfur has 6, and there is only one sulfur, so that's 6. Oxygen, again, you need to count along the line where you have oxygen is, and count from left to the right, 1, 2, 3, 4, 5, 6. And that's valence electrons, and we have four such oxygens. That's 24, and altogether we must have 32 electrons. Whenever you have an acid, first leave out hydrogens for next step, and our central atom is the one which is present in least number. Sulfur is present in least number, so I have sulfur in the middle, and have 4 oxygen. I wrote down the rules in my lecture note. Then give noble gas configuration to the outer atom. In this case, oxygen, it needs 6 more electrons. So each line would be 2 electrons or a pair of electron. 2, 4, 6, 2, 4, 6. Now you add up all the valence electrons that you have assigned. 8, 8, 8, 8. That account for all 32 electrons. That means my Lewis structure is right, except that I need to add 2 hydrogens. You can pick any of these 2 oxygens. So if I pick this oxygen, we just write down a little differently now. One oxygen here, and other one I can pick here. And that's H2SO4, Lewis structure for H2SO4. Now I'm going to show you another example how we can write down a Lewis structure quickly if it's coming from an organic compound. Organic compound usually have bigger formulas, so it takes time, so I'll show you how we can quickly write down Lewis structure for organic compounds. This is number 47F, same chapter, chapter 8. NH2OH. Something you need to remember when you write down organic compounds, carbon would have 4 bonds. This would save your time. Carbon, neutral carbon would have 4 bonds. Nitrogen would have 3 bonds plus 1 electron pair sitting on nitrogen. Oxygen normally would have 2 bonds plus 2 electron pairs sitting on oxygen. If you remember this, then it would be a lot easier to write down Lewis structure for some organic compounds. Okay, nitrogen in this case, I write down nitrogen and distribute 2 hydrogens around the nitrogen. And then NH2, and I need a pair of electron here, so that altogether I have 8. Oxygen, H. Or you can just draw lines for a pair of electrons, which often you can better see from a distance. So you can account for these electrons if you add up all these valence electrons, but this is the right Lewis structure for NH2OH. Quite often students get confused how to write down. For example, this is another question. Say C2H4. How do I write down Lewis structure? Again, this is an organic molecule having 2 carbons. I distribute hydrogen like equally, so each carbon would have 2 of them. That makes C2H4, but look at here, this carbon doesn't have 4 bonds. This carbon also doesn't have 4 bonds. It doesn't have any other hydrogen. So what that means is you need to make a double bond. So this is the right Lewis structure for C2H4. Now, often we ask you that how many bond pairs are there or non-bonding pairs are there. This pair of electrons sitting on nitrogen is non-bonding pair sitting on nitrogen. There are 2 such pairs on oxygen. They're called non-bonding electron pairs. So non-bonding electron pair. The pairs of electrons are solely on a particular atom are called non-bonding electron pair. In the exam, I'll specify that give total number of non-bonding electron pair on nitrogen or on oxygen or on a central atom. Okay, next topic that I would like to cover would be resonance, bond order, and then formal charge. This would be 7C. I kind of lost track of these numbers. NO plus NO2 minus and NO3 minus. Okay, now, you first get the valence electrons. Let me show you one of these. NO, nitrogen has 5 valence electrons. You can look at nitrogen and count from left to the right, and you'd find there will be 5 valence electrons. Oxygen has 6. Now you take away 1 electron, so it's 11 minus 1 because it's NO plus. So you'd have NO, give noble gas to this oxygen, 8. Then I have 1 pair, that's 10. But this nitrogen doesn't have 8 electrons. So bring 1 pair from here, another pair from here. So you get NO3. So that's NO plus. What kind of bond order we have? Bond order is 3. Or what kind of bond type we have? 3 means triple bond. 1 means single bond. So this has triple bond between nitrogen and oxygen. In the same way, you can calculate, I'm just showing you NO3. add up all the valence electrons. Let me do this. NO3 minus, nitrogen has 5, each oxygen has 6, and I have 3 of them, 18, it's 23. I have an additional electron because of this negative, so that makes 24 electrons. So my central atom is nitrogen, and there are 3 outer atoms, and give noble gas configuration to the outer atoms. That makes 24. But nitrogen doesn't have noble gas configuration. So in order to make noble gas configuration, make a double bond here. So don't get confused with this structure with organic structure. What I said, that nitrogen normally would have 3 bonds. And this is not a neutral. This is NO3 minus. So this has 4 bonds. Now, there are 3 possible structures. We call them resonance. This double bond could be here, could be here, or could be here. So let me show you those structures. And double bond O, O, O. This would have 2, 4, 2, 4, 6. This is going to be structure 1, this is structure 2, and the third one is going to be here. And O, O, and then you'd have a double bond here. 4. So this is the third structure. Now what's the difference between the first one and this third one? In first one you have only one structure possible. Nitrogen having a triple bond. Here there are 3 possible structures where the double bond is moving around in 3 locations. Here, here, or here. That's what these 3 resonance structures shows. That double bond, the second bond is moving in 3 places. So the contribution coming from the second bond would be 1/3 because it's going to 3 places. So what kind of bond order we have? 1 and 1/3. This 1/3 is because of the moving double bond. 1 is fixed. The second one is moving in 3 places. So the bond order for this is 1 and 1/3. So I don't have space here, so let's write down bond order on the top. Equals to 1.33. Because of the resonance where the double bond moves down. Here the bond order is 3. So if I ask you which NO bond will be shorter, it always goes with the bond order. Bond order tells you what kind of bond you have. More bond, greater attraction. 3 bonds, greater attraction. 1 and 1/3 bond, smaller attraction. So NO would be shorter. NO distance shorter in this case, and this compared to NO3 minus. I'd like you to work on NO2 minus yourself and see where you place NO2 minus compared to NO plus and NO3 minus. So that would be good practice for you. But I can give you the answer. I think you're going to get 2 resonance for this, and bond order is going to be 1.5. Next, I'm going to explain to you what is formal charge, and by picking one of these structures that we have already drawn. So formal charge. Let's now redraw one of these 3 structures, and double bond O, 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 and then you have 2, 4, 6, 8, just to make sure we never go beyond 8, because these are not going to, these are going to follow Lewis's rule. which gives 8 electrons around each element. Okay, let's calculate formal charge on each center. Now first, let's give numbers. This is 1. This oxygen, let's call it 2. And this oxygen, 3. Oxygen 1, how do I get formal charge? First, find out how many electrons you have on oxygen. 1, 2, 3, 4, 5, 6. And take half of the bonded electron pair. 7. So 2, 4, 6, 7. 6 are solely on oxygen, which is non-bonding electron pair, and 1 pair is being shared, so take just 1 electron out of that. So 2, 4, 6, 7. So oxygen 1 has 7 electrons. And how many is supposed to have? From periodic table you find out the valence electrons. Go to the line where you have oxygen and count from left to the right. So you'll be counting like this: 1, 2, 3, 4, 5, 6. And you find that it's supposed to have 6. To have 6. And that's valence electrons. So it's supposed to have 6. Now it has 1 extra electron. So this has extra electron. Because of extra electron, it gets -1. So you assign -1. That's the formal charge. So let me circle this. Now let's count this oxygen, oxygen number 3. 2, 4, solely on oxygen. And half of these, 5, 6. So this oxygen has 6 electrons, and it is supposed to have 6. So the charge is 0. But there is no extra electron. Now let's now focus on nitrogen. How many electrons we have altogether in this structure? Again, 1 coming from this single bond, 2, 3, 4. It has 4 electrons. Has 4 electrons. And how many it's supposed to have? By looking at periodic table and counting from left to the right, you'd find that it's supposed to have 5. 5 valence electrons. Supposed to have 5, but it has 4. That means it lost 1 electron in reshuffling. So nitrogen will be +1. So in the same way, if you do the calculation for O2, this is going to be -1. So -1 +1 -1, 0. So that's distribution of formal charges. All of them, when you add up, it's going to be -1 because NO3 has charge of -1. Otherwise, you have made a mistake in this calculation. So the last type of problem for this review session would be heat of reaction calculation from bond energies. So delta H of reaction from bond energies. Now I'm going to do problem number 69A. This is from chapter 8. For this, you'd need bond energies, and in exam, I'll copy these values just to save you time. And the final product is HO. CH2 CH2 OH. So you get a heat of reaction calculation from bond energies, basically bond breaking and bond making energies. Book has a table, I think it's table 8.4. So look at the table 8.4 for your practice. That gives all the bond breaking energies. That means if I have something that I want to break, I need to put some energy. And those energy values come from 8.4. Now, this is like building a model. I have this to begin with, this to begin with, but I need to end up with this. So basically break it and make it, finally you end up with this. So what do I need to break here? Here, because I have C double bond C on the left side, but there is no C double bond C on the right side. That tells me that I need to break this bond. From that table, I find out that it needs 614 kilojoule of energy to break this double bond. You cannot just break single bond, one bond out of two. When you need to break it, break the whole thing. So carbon-carbon double bond breaking energy is 614 kilojoule per mole. And that's assumed that we are using per mole. Now, there is no OO bond on the right side. So that means I need to break this bond. And that also needs energy, and that amount of energy is 146 kilojoule per mole for oxygen-oxygen single bond breaking. On the right side, what do I need to make? If you look carefully, CO bond. We didn't have a CO bond, so we need to make it. Now, bond breaking energy is given in the table. The bond making is the reverse process. So you have the same magnitude, but the sign gets changed. So this would be minus 358 kilojoule. The bond breaking energy is given as plus 358. I made it minus because we're making this. We're connecting them together. Same is the case here on this end. Minus 358 kilojoule. We also didn't have a carbon-carbon single bond. That's also we're making. So that needs 348. This gives off 348 kilojoule of energy. The energies are pretty close to each other. Okay, now we're pretty much done. We need to break these. We need to make these new bonds, which I'm showing you with up arrow. So what is the total energy change? That gives me the heat of reaction. It will be given by just the sum of all these numbers. 614 plus 146 minus, there are two such 358, 2 times 358 minus 348. And that gives me 3 or 4 kilojoule. I want to caution you that sometimes you may have 2 in front of this. If I have 2 in front of this, that means I need to multiply this number by 2. Or I have 2 similar bonds that I need to break. Again, you need to multiply by 2. Just like here, you have to multiply by 2. So, pay attention to the fact, when you're making a bond, use the same value of the energy, except the sign gets changed from positive to negative. For bond breaking, these are the values directly from the book, without changing the sign. These are all positive. And then finally you add up, and you get heat of reaction. And there would be a question like this in the exam, so make sure you do this kind of problems and prepare yourself for this exam.